Thank you that you are here, because it's the last talk and the day was really long and probably you are excited during other talk, but anyway, you're here to hear about security. Wow, I'm proud of you, really, because I'm really tired. Probably you are too. My name is Anastasiia. I talk about mobile security for last few years, and this my talk will be a little bit different. Instead of discussing some discrete method, we will assess a real-world application. We will investigate its security risks, and we will come up with a solution for those risks. And most important, we will do it in a special way, in a way where most control is in our mobile developers' hands. And no failure on server side would possibly introduce any security risks to our system. Actually, this explains a bit the name of my talk. I work in a small mobile development company called Stanfy in Kyiv, Ukraine. I do write iOS code. I also do write a server-side code, but I'm a contributor to one open source cryptography library called Themis. That's why I know a thing or two both about mobile and security. Be brave. It's security talk. It may be complicated a little bit for you, but no worries. I have a lot of links, lot of slides, so it's okay if you won't understand some pieces. You can Google for them. I will provide links. I will share slides. Google, watch video, and make up your knowledge base. What we will talk about today? We will discuss what are risks and threats in our mobile infrastructure. We will emphasize trust model. Whom do we trust, and what exactly is a trust model? We will discuss a sample application and build security model for this real application, right? We will look on the code and the libraries that will help us to implement the things. And of course, we'll discuss some attack scenario on our security model and some improvements. What can we do better? Okay, let's get started. And the main question is, why should we think more about mobile security? Most of our users, they live in a magical world, in a world where things just happen and they think that they are safe out of the box. But remember Pegasus, the remote jailbreak just by pressing a link. The Pegasus is a rare bird and there is nothing we can do about it, but it doesn't mean that we shouldn't put any efforts in security. Because if we don't, attackers won't need Pegasus to steal our data. Most users trust sensitive data to our application without understanding, do we protect it well, actually? And it's up to us how to implement security. Most security talks are based on a model when they discuss some discrete methods, and security guys who are like really security specialists and cryptographers, they tend to look on the world through the lens of security. And for them, our mobile application is just, like a spherical cow, it's just something. But in security itself, it's a set of methods, a set of rules like do these, and don't do that. But we understand that it's not exactly so. We are not growing spherical cows. We are building real-world applications for real users. Right? And that's why we should discuss security in a proper way. Let's take a look on the process how we build applications. Starting from the user problem, going through the application flow, building this flow feature by feature, right? And here we are writing the code. Actually, the security process, it's quite similar. Security starts from the risks and threat model and progresses in a similar linear fashion through the secure methods to the implementations and close to the instruments and libraries. Please note that the most popular question, what library should I use, is the end of the sequence. We really should start from risks, not from code pieces from Stack Overflow. Okay? This we will discuss during our talk, starting from risks analysis. The problem here that it is secure as a statement is invalid and irrelevant. It is as fake as presenting our application like a spherical cow. Instead, we have a statement, it is secure against certain risk model and certain attacker. And this statement has a little bit more sense for us. Here is an example of proper thinking. It's precise and it leads us to practical outcomes. There is no such things as absolute security. You just need to do more and to pay more attention that it will take for attacker to break your system, right? The threat and risk model is something kind of specification in the world of security, but for us, for engineers, specification is more like a positive thing. Do this, implement this, let user do these things, like describing the features. In the world of security, specification is a more negative thing. Prevent doing this. Don't let attacker do this. All these negative sides. Make sure that some things won't happen. The real-world risks, they are obvious. If your data is leaked or being tampered, your reputation will be damaged, you could get sued, and in any way this will lead to a financial damage, even if this financial damage is an extra cost for rewriting your application because it was broken. What are the impacts of these risks if they turn into real accidents? Whatever the attacker used data for, it will lead to a significant damage inside or outside your scope of responsibility. It's not like we are just engineers. Yeah, it won't hurt us. It will. It definitely will. And basically we are dealing with three risks. Data leakage, data tampering, and identity theft. For all these risks, we can implement the countermeasures. For leaks, we should encrypt data, so it's pointless to steal. You still can steal it, but it's encrypted. It's kind of rubbish. For tampering, we should store data securely and make sure to provide so-called integrity verification. Make sure that the data, if the data will be changed, there will be a trace. We will be able to understand that the data was changed, and now we can't trust it. And for identity theft, of course, we are using the authentication methods, right? All of you know all these methods, symmetric, asymmetric encryption, and different kinds of authentication, for example, multi-factor authentication, other things. We are heading to the encryption. Encryption is very important in the security world. It's a kind of basic idea, and it's very tricky because it differs from other security measures. Unless you know the secret, no matter how much you want, how much effort you will do, but you can't read protected data unless you know the secret. This is what encryption is about. We talked before about trust model. So let's say again, what is a trust model? We talked about risks. Now we're talking about trust model. Trust model is basically whom do you trust in your system. And in our system, trust model is really simple. Everything is broken. Trust nobody except the user. And according to this trust model, we will implement our security methods and our protection methods. Let's combine these things. Risks dictate threat and trust model. In turn, threat model affects on choice of instruments, and trust model affects on implementations of this configuration and implementation of these instruments. Code and libraries, they make sense only when we are talking about exact risks. Now let's move to practice. For this we will need a hero. And in our case, a hero is not some kind abstract Alice or Bob. In our case, the hero is a real user. Okay? Now I need a volunteer for a minute to stay here and to help me a little bit. Don't be scared. Just raise your hand if you want to be a volunteer. Yay, please come here. And you will need a microphone. Can you please give him a microphone? Yes. Awesome. Hello, thank you. Yeah, Duck. Mr. Duck. Come here, come here. What's your name? Okay, Mihaly. Please tell me, do you have an iPhone?
Yes.
Yes, okay. Most of our users do. If our user has iPhone, it means that he can install our application. And in this case, the fact that he will install our application means he has some trust to us. And you remember the trust is very important. What else do you have? Probably you have some private data you want to keep in secret, right? Probably some photos. Well, okay, it may be not photos, it may be scans or some important documents, right? And and of course, you can imagine the password for keeping your data secret. Imagine a password. You can tell it like loudly. Just imagine some passwords for your data.
Cow 123.
Awesome. That's a typical password, right? Our users have. We need to protect them. We need to protect their data because it's very important for you not to put this data, your private data, not to put it anywhere, but to put it in a safe place, right? To keep it secure, because probably you may be a little bit paranoid, and you need this tinfoil hat to protect you. And here we are, the application developers. We will implement this tinfoil hat in our application to store your data securely. Okay? Thank you. You can grab this hat and go to your seat.
Thank you.
You're welcome. Let's continue. So, what we have? We have a user that is using our application, so he has some kind of trust for us. He has some private data. He wants to store it in a secure place. He can imagine a password. And of course, he is a kind of paranoid, a little bit, because he really is into this security stuff and he really wants to see, this small lock icon near his data. What we will do, we will create a special application. Well, actually, it's kind of yet another application for traveling, because you know all these problems you can have while you're traveling. For example, you can lost your passport. It's really pity. So wise people, they make a scan copy of important documents to store them somewhere, but scan copies of your passport is kind of private data, and you want to store it secure. You don't want to put it like anywhere. And we'll create application for this. Basically what our application do, it's really simple. You can take a picture, you can save it somewhere, and you can read it from someplace. This is the architecture map for our application. User takes a photo, application sends this photo via network on the server. Server stores the photo somewhere on the storage. Really easy. Now let's take a look on threads we can have in our system. Well, it's not a very detailed model, right? Let's imagine all possible threads we can imagine, like everything, well, almost everything in the world. Looks much better. Including remote jailbreak, including rubber hose cryptanalysis, a lot of risks, a lot of threats our simple application, simple system have. The question is, can we handle all the threats? What can we do if user forgets the password? What can we do? Is there anything we can do if user tells his password to someone? Someone using rubber hose cryptanalysis, right? No. We can't handle them all, unfortunately. So let's leave only those threads that we can handle, actually. Only 4 of them. T1 and T4 means that the data may be stolen or changed. It applies to the server, application, and the storage. T2 means the transport may be intercepted. T3 means the transport may be intercepted, the data may be redirected, and it may be changed. For every thread, we will implement and discuss a countermeasure. Let's talk about them one by one. T1 and T4 means the attacker can steal your data, right? It's kind of easy. It's not so easy when we're talking about iPhone, because you need to use some weird applications like iPhone Box. As you remember, it was working fine till iOS 9.3.2, but on iOS 10 it's not really working, but let's wait. There may be another application that will allow us to steal data from the app, but it's really easy on the server side. What we can do? When we are talking about stealing saved data, we are talking about symmetric encryption. So we encrypt user data, so if anyone steals this data, it just encrypted something. And if you don't know the secret, you can't decrypt it. Thread T2 is passive man in the middle, where attacker collects data during transmission, and it's easy to emulate using proxies. For example, using Charles proxy or Burp proxy. I'm sure you have tried at least once to see what's going on in some application. When you actually were an attacker for this application. What should we do? As soon as we are talking about transport layer, we should remember about asymmetric encryption to ensure the identity of both parties talking. However, it's much safer to use asymmetric encryption to derive one temporarily so-called ephemeral key, right? Do you remember the perfect forward secrecy term from Facebook talk, Facebook end-to-end encryption talk? Actually, the perfect forward secrecy means that you encrypt communication in different sessions using different temporal keys, and if one key is leaked, you can't decrypt all your conversations. You can decrypt only one session. Conversations that were before, you can decrypt them, and what is more important, that conversations that will be, future conversations, you can't decrypt them too. Let's talk about thread T3. It's active man in the middle, which means that attacker pretends to be a server. As example, we can show China with their golden shield firewall. They can compromise SSL connection by proving fake SSL certificates. What should you do? Of course, as it's also networking, we talk about asymmetric encryption. But this time we're talking about asymmetric encryption plus certificate pinning. Go back. Plus certificate pinning. I'm sure you know what is certificate pinning, right? Please raise your hands who have implemented certificate pinning at least once in your application. 1, 2, 3, 4, 5, dozen, maybe 1/4 of our audience. Awesome. For those of you who still didn't implement these things, it's really easy. All you need to do is to pin or to save public server certificate inside your application. So during network communication, application will compare pin certificate with server certificate, and if these certificates they don't match, application will like, no, I won't talk to the server. There is a lot of theory. You can pin different parts of the certificate. You can read about it in a link I probably provide you like on the last slides, but it can be really easily done on in the code. So let's put these protection methods on our map. Looks really nice, right? We're using symmetric and asymmetric cryptography, we're using ephemeral keys, and we're using certificate pinning. But you know, encryption means keys, and keys means trust. Let's recollect our trust model. Whom do we trust? The user, or maybe the user only, right? Going back to our application. User takes photo and it's a plain data. It's a private data we will protect. Application encrypts this photo using symmetric encryption, wraps it into symmetric container. Then application and server, they initiate a secure session connection using asymmetric encryption, derive one temporally symmetric key, and encrypt already encrypted container one more time using this key. Application sends this container to the server. Server decrypts first layer. Our container is still encrypted, and it's stored on the storage in an encrypted way. By the way, there is one component I haven't talked before. On the bottom, these 3 letters. There are cases where there is no trust established between the client and the server, or client and the transport, or all these things. But there is a method to verify server honestly, even all cryptography fails. It is known as zero-knowledge proof protocol. It's a really simple mathematical protocol which enables 2 parties to compare pre-shared secret without transmitting this secret or any hashes derived from this secret via network. ZKP will help us to ensure that server really has our photo. You can read about ZKP in that blog post. You can ask me, you can read in Wikipedia, you can ask me. It's really after talk. It's really simple, right? But for now, let's imagine it's just a mathematical protocol, and we are able to understand if second party has the same pre-shared secret without transmitting it via network. We will use ZKP. Going back to our data model. User has a password. An application never stores this password. Instead, it transforms it into secret key using KDF. KDF is a key derivation function. It's yet another simple mathematical function that allows you to take in any string, and as output, it creates a cryptographically good key. So we don't store password anywhere. We transform it into secret key. What else do we have? We have a photo. Photo is a sensitive data which is private, which we're protecting. But there should be some pieces of public information that we will use. In our case, we have two pieces of metadata. Metadata M1, they are public, and metadata M1 is a timestamp plus CSV of the photo we calculate inside the application. Metadata M2 is the name of the photo, and we ask user to put it inside the app. Both application and server will generate key pairs, public and private keys. So we have mobile key pair and server key pair. And of course, we remember that we use SSL pinning. So mobile application also has public server certificate pinned. Let's put all these things on our map. This is how it looks like. The password is only in user mind. Application has secret key, sensitive data, which is private, two pieces of metadata, which is public, mobile key pair, and server has server key pair. That's really easy. And this is the most important slide on the whole presentation. This is a hierarchy of trust. We use secret key derived from user password to create encrypted container. We put everything in this container. We put keys, any other keys. When user wants to send photo, we get a secret key, create symmetric container, wrap his photo. Then we initiate secure session connection. We get our private key, so our public key, create asymmetric connection, derive one symmetric key, and wrap again the photo. The idea is that everything is being derived from the user. But we don't store user password anyway. Let's take a look on the application flows. Next slides will contain some pseudocode. I use them just to more understanding. I use the terms from Themis library. I like the names actually. Secure cell is a symmetric container, secure session is a asymmetric session, and secure comparator is a ZKP implementation. Of course, you can use any library you prefer, right? We talked before that code in a whole security process is not so important as the whole analysis. So you can use any library you prefer. The only thing that, as much as I'm aware, the only ZKP implementation on iOS is inside this Themis library I'm working on. So, let's take a look on two examples. First of all, sending photo on the server. It's really easy. Stage 1 is preparing the data. Application asks user password, it derives secret key, it encrypts photo, grabs two pieces of metadata, calculates timestamp plus CSV, and asks for the name of the photo, and saves them, and drop original private things from memory. Step 2 is a session connection. We establish secure session between the client and the server using client private key and server public key. We derive symmetric key and wrap ephemeral symmetric key and wrap our container one more time. We send encrypted data on the server. And the third stage is really important too. It's the session termination. We'll need to terminate the session when upload is okay. Why? Because in the next photo we will create another session and we will generate new temporary key. So it's important to terminate the session. Only these 8 steps. It's kind of easy to send secure photo on the server. Reading photo is also easy. Stage 1 is the trickiest one actually. Application creates a secure session connection in the same way, but on the step 2, we need to make sure that server has our photo. We initiate ZKP protocol using metadata M1 and ask server to confirm that it has metadata M2. What does it mean basically? Application sends timestamp plus CRC on the server and asks server, do you have the name of this photo? Please prove that you can find the name of the photo using credentials I sent to you. But don't send name via network. If ZKP stage is successful, it means that server really has our photo, at least metadata for this photo, and we can ask for this photo. Only on this stage, on next step, we ask, please send us photo back. But if you remember, the photo is encrypted. So when application receives the photo, it needs to decrypt it. This is why we ask user password, we create a secret key using KDF from this password, and we decrypt the photo and show this photo to the user. 7 simple steps to read data from server. I have prepared some code pieces. I'm working actually on, there is a real application for this, a real example on Swift and Python, client side and server side. I will publish it a little bit later, because I'm still working on it. But I have prepared some code pieces for you. Just don't read them very carefully, just look at the amount of code. This is a key generation. This is creating symmetric container and encrypting data, right? This is decrypting that container. This is initiation of secure session and sending and receiving data using this session. It's written on Swift. It's really not many code. It's easy to implement in your application. But we can move all the things to a next security level. We can make everything even more tough. From the application side, we can use not one password for the whole application, but we can ask user to set a password per each photo, right? And if each photo will has another password, we increase security guarantees. So if one password will be leaked, only one photo can be, only photos that are encrypted using this password can be decrypted. We can improve communication too. This mechanism is known as repeated authentication. This is a method to ensure that on every step, our server is the same that it used to be on the previous step. It makes our communication stateful. It means that we should check, before sending new photo, we should check whether server has previous photo. Because probably we are under attack and probably our server is not our server anymore. How to do it? Before sending new photo, application selects any random photo from the list of already sent photos. It uses its public metadata M1, so basically we are doing ZKP again, right? We are using metadata M1 timestamp plus CSC, we are sending it on server, and we are asking server, please confirm that you have the name of this previously synced photo. If you do, it means we can trust you. At least you are the same that you were during this communication. If server proves it has metadata M2, application sends next uploading request. It's called repeated authentication. Let's take a look on the scenarios of possible attacks, because it's very important. We are not building like something in a vacuum. We are prepared for different attacks. First one is active man-in-the-middle, but without hacking the server. It means that attacker tries to redirect network traffic to his own server, but he doesn't have access to public and private key of the original server. But we are pinning server certificate. It means that if somebody wants to be like a man in the middle between us and the server, but doesn't have the same certificate, SSL pinning, which allows us to see that certificates they are not matching, and the application will just refuse this connection. We'll see some kind of network error, like no, something bad has happened. We are not talking with our server. Certificates are not the same. Let's imagine scenario when attacker has access to our server. So he is able to get both private and public certificates. And actually he pretends, like during man in the middle, he pretends to be our server and he has everything for it. In this case, application will communicate to the server, but take a look on what we send to our server. We are sending encrypted pieces of data, and we are sending public metadata that is kind of useless. Timestamp plus CSC and the name of the photos. It's not anything private, it's not anything sensitive. In this scenario, yes, application is communicated with the attacker's server, but it feels like we are talking with like Amazon S3 bucket, but it's free. We don't need to pay it because somebody stores encrypted files. Maybe the worst scenario we have is actually denial of servers. Attacker feeling really annoyed after his series of miserable failures, he may start flooding our server with connection requests, with uploading requests, and it may be a problem. But denial of service, like it's 2016. It's really easy to handle denial of service. You have a lot of methods, you have a lot of instruments like IP monitoring, like IP blocking, like using third-party solutions like Cloudflare, using decent firewalls. It's easy to handle denial of service. So in our system, we have different attack scenarios, but the worst scenario is really as bad as denial of service scenario. In any other scenarios, attacker won't have access to private data and decrypted private data. Let's finalize our thoughts. First of all, people still think that cryptography is very computationally expensive. Scripted languages and questionable frameworks, they affect performance much worse than running expensive crypto. You might take a look on those links on benchmarking of Themis and Python server. And if we are okay with writing backends on languages like Python, we definitely can handle this expensive cryptography. Moreover, good cryptography standards, they become some kind of industrially wise, and they start having hardware support, like IIS. If we implement proper security models, sooner or later, we may have more support in it. It may be even more easy for us. And let's talk about Apple. Apple really enforces good security practices for us. All of you know about new Apple transport security policy, right? Use HTTPS everywhere, drop all ciphers, all these things. If you still don't, you can read those awesome blog posts by Nabla explaining how we need to change our code to be compatible with this new system. Of course, all of you know that starting from iOS 10, we need to add new strings in our plist files when we are accessing private data frameworks. If you still don't know, there is yet another link for you. And the basic idea is that Apple really cares. This slide is from Black Hat conference. It's a hacker conference. And the Ivan from Apple was there, and he had a talk, and he was talking about really complicated security stuff inside iOS. I would recommend everyone to read the slides, the link is there, or at least to watch the video, maybe both, because it's really interesting, and it's much more complicated than my version, right? But the important things I want to point out, that Apple follows same principles as this talk, derive everything from user trust, from user password. So the key points. As you can see, user-centric trust is something quite simple to implement. 8 steps there, 7 steps there, really small piece of code. But it's kind of very difficult to hack. We can imagine a lot of threats, a lot of attack scenarios, but in worst case, attacker may have a pile of encrypted data and some useless pieces of public data. But to make sure that this system works in your head, you may want to reread the slides. Because if you don't think about security as a whole system, but if you're still thinking that it's just methods or just a code pieces copied from Stack Overflow, it won't work. You need to build step by step a solid system with a lot of fences, with a lot of security perimeters in your application, in your client-server architecture. I have prepared a small list of slides for your home reading. Let's start with my other talks. If this talk was a little bit complicated for you, you can check other talks. They were not so complicated. They have funny images and sites. If you're not really into security, if you're not really into cryptography, you can read them to understand what is symmetric, asymmetric encryption, what is perfect forward secrecy, what is ZKP, what is synchronization, compartmentalization, and other security stuff. Also, I have put additional reading by Apple. Just see, we have on latest WWDC, we have at least 3 sessions that Apple was talking about security and privacy. It's really important now, and Apple forces everyone to understand what's going on and to implement security methods in your applications. And of course, this is a slide link to slides, that Black Hat slides from Ivan. And the next slide is additional reading from over the internet. You can read about ATS, you can read about iOS 10, you can read about ZKP. And if you're interested in Pegasus, and if you still haven't read anything about it, there are 2 posts. What was this attack about, and what ideas, like what we learned based on this attack. So, thank you. If you have any questions, please feel welcome. If your question starts with, in my application we have, maybe let's discuss it after my talk, like one-to-one, okay? Not to make it too long for everyone to wait. Because every system is kind of unique. I am okay to discuss it with you. I'm okay to help. Just you can go to me and ping me, write me. There are a lot of things in my Medium. I post a lot of things in my Twitter. So a lot of ways to ping me. Okay. Any questions? Right.
Thank you. Спасибо. Do you think it makes sense for any application or for some applications to check if the device is being launched is jailbroken? And do you know any reliable ways? Because recently there are some patches like TS Protector, for instance, that is hard to bypass to make this check reliable. But sometimes in some use cases we don't want user to access some levels of access to some data to unlock some content of our application. But with a jailbroken device it's easy to do. So as I am aware, Apple doesn't tell anything about this. So what is your opinion about this issue?
Well, jailbroke applications is something like if we have a user and we smash his fingers. Having jailbreak application means jailbreak device means that attacker can do like anything, right? And yes, Apple has no stable way to detect if device is jailbroken. And yes, you need to rely on these many mechanisms that are changing from iOS version to version and all these things. But the idea is that if you take into consideration that device may be jailbroken, you start using a little bit other algorithms. For example, instead of just putting a key into keychain, because keychain can be readable if device is jailbroken, you can, instead of remembering storing key, you can generate it on every run, right? Not to store it somewhere, but to write a mathematical function that will allow you to generate the same key using the same input parameters. So your application won't store this key, but won't store this key, but it will generate it, even if the device is jailbroken. Only accessing to a Pony debugger or any other debugger to the memory, which will allow attacker to read this key from the memory.
Thank you.
Hi, thank you for the talk. It was really cool. I wish everyone could get such a tinfoil head. If I understand correctly, this protocol works also if you lose a device, right? You could get the data on a different device. Is that true?
You mean this whole system?
Yeah. So if I drop my phone in the water and get a new phone,
because we rely only on user password. I mean, only on the password in his head.
Right. So how would the zero-knowledge protocol work on a new device if you don't actually have the metadata on that device?
Zero-knowledge protocol is based on pre-shared secret. So what you need to do first is have some pre-shared secret. Yeah, something that you store in your application before you start all this communication. And the idea is that you just compare, you make a set of there and here changes, like there and here operations, to make sure that each party has the same key. If you really want to know how it works, we can describe it using a cave. It's a typical description, you can read about it in the Wikipedia. I can continue if you're interested. Are you interested in ZKP? Yes. Okay, so imagine a cave. Right, really physical cave that has an entrance and it has a secret door in the middle of the cave, and the door is locked and you need a key to unlock the door, and it has two ways to go to the entrance: cave, door, and two ways, like left and right, okay? Probably two exits. What we have two parties, like anyone, like Paul and Mike, Alice and Bob, anything. Two parties, they have something, they have some knowledge, shared knowledge. In our case, one party has a key and it wants to prove to another party that it has a key. So let's say them Alice and Bob. Bob go into the cave, to this door. He can unlock the door using the key. Alice is staying out of cave, and she wants to make sure that Bob has key. So she is telling like, Bob, please go outside the cave from the left exit. If Bob really has a key, he can unlock the door and go to the left exit. Like, Alice like, okay, I ask you go to the left, you go through the left. Okay, it matches. But maybe like mistake, maybe it's random. Bob, please go to the right door, to the right exit. And Bob gets into the cave, use this key to unlock the door and go to the right. Alice like, okay, I ask you to go from the right exit and you do. Okay, please go from the right again. And Bob like, okay, I still have a key, I can go from the right. And using this kind of checks without actually showing a key. Bob doesn't show a key. He just do what Alice wants. Using a set of these checks, Alice can say, okay, I believe you. You really have a key. This is like a typical description, but in our case, key is something shared, and this left and right is a result of mathematical functions. For example, if we are talking about elliptical cryptography, this left and right is the projections of the point on elliptic curve to the different ASICs, right? This is basically how it works. Mathematically, it requires from 6 to 8 checks to have a 99.999% sure that this party has the same key. I hope it's more clear now, but if it's not, just ask me again. I know more examples. Or read that ZKP without magic blog posts. It uses some other really mathematical formulas and mathematical examples. The idea is that if you need to do 6 or 8 checks before communication, it may be longer than without doing them, right? But as we talked before, if you have server written on Python or some scripted languages, probably you will do these checks more fast than all your things on the Python server, right?
Just an additional question, but what is wrong with just exchanging the hashes of these keys?
Because you're exchanging them via network, and if you don't trust the network, these hashes may be intercepted.
Okay.
And here we go, the man in the middle.
What use of the hash can attacker have?
The same as as you use them. I mean, if you use hashes for something, and what we are not talking about hashes, we are talking about keys. Keys are kind of private. We don't want to send them via network. ZKP is used to determine if server is the one, if it has pre-shared secret, if it wasn't changed before. I mean, if it's still the same as we talked before, right? It's like a pre-stage. It's stage before actually sending encrypted data. We just want to be sure whom are we sending this data. That's why we're using ZKP. Right, one more question. 2 more questions, okay.
I would like to ask you about your opinion. What is more dangerous, to keep few but very clever passwords in my mind, or to share many passwords but encrypted between all my devices in some cloud service?
It's complicated because every solution has its own risks, right? What risks for you is bigger, to have sudden amnesia and forget all your passwords, or if the service you're using will be broken, right? You just make this decision. If you're okay, if you're like, what if I will have amnesia? You can put it somewhere, but be prepared that if this system will be broken, you need to change your keys. So it may be nice to put them somewhere encrypted, but to change them time to time. Because usually, the problem is that when some system got broken and we have these news, these titles, system was broken again, many, like millions of emails plus passwords were leaked. Usually this message is on not the same day as the leakage. It may be like years between. And if you're still using the same password, if you didn't change it, attackers may use your credentials during this long period of time. So if you do, you can change these passwords, your passwords, even if you store them on some place. And yes, please.
Thank you. What do you think about code obfuscation, and what very simple things I can do to very simply improve my app security?
Unfortunately, there is no simple solutions, right? As we talked before, security is kind of race. If you need to do all things you can to ensure that it has like a proper level, better that you put really much effort into it, and probably if you put it more than attacker, your application won't be broken for some time. What I think about obfuscation. Obfuscation is a nice idea if you don't stop on this step. So only obfuscation it's not useless, but it's like a simple protection methods. If you have obfuscation only, you're like building a tiny fence. Of course, this tiny fence will protect you a little bit, but someone can just, step over this face and it's useless. What you need to do, basically, you need to build many fences, really a lot of them. And this case, somebody will step over one, maybe over two, but the more you have, the more difficult is the route. Okay? So you can use obfuscation, but don't stop on using obfuscation only. You definitely should implement some encryption of users' data because users' data is like the most important thing in the world. If your application has deal with really users' data, with user-generated content, it's better to keep it safe. Not every application needs all the things. If you're implementing yet another Instagram for cats, you probably don't need all these security things. But if you're working with user data, you do.
Thank you.
You're welcome. Thank you for your questions. Any more? If not, we can... Yes, one more. I realize that is it the last talk, right? Yes. So I totally realize it is the last talk and tram party. It's what we are waiting for, so...
Okay, will your system work offline?
Will our system, you mean all these...
For example, I can store some data and then, for example, in the plane, I want to show my photos to my friend. And what happened this way?
Yeah, you need to make small improvements, because in my case, application doesn't store the photo, but you can also store it in an encrypted container. I mean, you won't store plain text, you don't need to store plain text in any case. But if you store an encrypted container, so for you to show photos to a friend in the plane, application will ask you to input the password, use it to derive secret key, and decrypt the container. You can do it.
Okay, and another question which derived from this, can I store a huge data in the storage, for example, for some gigabytes?
Do you mean that? What exactly do you mean? Can you store huge code, huge pieces of data on your iPhone? Yes, probably you can. It depends on capacity of your of your SD card, like, right? So if you have 32 gigabytes, probably you can't store 33. I think that you can't even store 32, basically. The problem is that with a whole encryption, that if you have really large piece of data, there is like single large piece of data, there are different algorithms that are optimized to encrypt large pieces. Because most algorithms, symmetric encryption algorithms, they can do it, but it will be long, and it will take a lot, of computational time, and it may take a lot of storage, like encrypted version of this thing. So you can Google for algorithms that are optimized for large files, or you can split these large files into different pieces that basically a lot of people do.
Okay, thank you.
Thank you. Let's finalize probably, right? So let's stop on this point. Thank you. Thank you so much for your questions.